Okay, welcome everyone to the 99th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Sondre Kvamme from NTNU Trondheim, and he will be talking to us about higher torsion classes and silting complexes.
Yes, okay, so let me just start by thanking for the invitation to give a talk in the seminar. So all the new results I will present are joint work with Jenny August, Karin Jacobsen, Johanne Haugland, Jan Palou, and Ippolito Trefinger. So the title of my talk is Higher Torsion Classes and Silting Complexes. And the goal of the talk is to explain how higher torsion classes give rise, or functorially finite higher torsion classes give rise to silting complexes, generalizing our result by Adachi-Iyama-Reiten. So let me start with the plan of the talk. So the first part, I will talk about the class of algebras, which arises in higher Auslander-Reiten theory, called higher Nakayama algebras. So even though they arise in higher AR theory, you don't need to know anything of that theory to understand the definition. They're just defined in terms of quivers with certain relations. Then I want to pose the question of understanding these algebras and what tools we have available. And with that as a motivating problem, I will introduce cluster tilting subcategories. And then in the last part, I will talk about higher torsion classes for cluster tilting subcategories and how they give rise to silting complexes. And then explain how this can all be computed very explicitly for the higher Nakayama algebras. So somehow this illustrates a bit the kind of slogan of what I want to advocate in my talk, which is that higher cluster tilting or cluster tilting subcategory gives you tools to obtain information about the algebra itself. In this case, it gives you a collection of silting complexes and therefore derived equivalences. So this also connects it with the somehow title of the seminar series on triangulated categories. Okay, so let me start bring this up here with higher Nakayama algebras. And before that, let me just recall the definition of classical Nakayama algebras. So fix K to be a field, AN will be the half algebra of the linearly oriented AN quiver, which means it has n vertices and n-1 arrows, like this, numerated from 0 up to n-1. Then we want to say what is I want to remind you what is a classical Nakayama algebra. So we say that algebra B is a connected Nakayama algebra of type AN. So all the Nakayama algebras I consider will be connected. So I will not necessarily repeat that adjective, but it will be like an underlying assumption. So B is a Nakayama algebra of type AN if it is a quotient of this algebra AN we defined by an ideal I, and that ideal I should be admissible. So admissible in this context for ideals of this algebra AN just means that it's generated by linear combinations of paths of length greater than or equal to 2. So it's contained in the radical of AN squared. So this tells us in particular that any admissible quotient of AN is a Nakayama algebra of type AN, and all Nakayama algebras of type AN are described in this way. So that's their definition. Now, it's a very old result in representation theory that tells us that such algebras can also be completely characterized by certain combinatorial data. And yes, and that's what I will present next. And it's the following theorem due to Herbert Kupisch from 1959. And it says that we have a bijection between Nakayama algebras or connected Nakayama algebras of type AN, isomorphism classes of those, and a set KSAN, And this set KSAN just consists of n tuples of integers indexed from 0 to n-1, so L0, L1 up to Ln-1. And these tuples should satisfy three conditions. They should first and foremost, the first term should be 1. The second condition is that all other terms should be greater than or equal to 2. And then the last condition is that at each step in this tuple, in the sequence, the value can increase by at most 1. So Li is less than or equal to Li plus -1 plus 1, and this here should be for all I greater than or equal to 1. They should exclude this particular case. Okay, so that's a small typo. And we call such a tuple of integers a cubic series of type AN. And then KS here just stands for cubic series. So this bijection is very explicit. So given an algebra or a Nakayama algebra of type AN, B, the associated cubic series is obtained just by taking the dimension vectors, the dimension of the indecomposable projective, right projective B modules. So here Pi is just the indecomposable projective right B module at vertex I. So we order these dimensions according to the ordering of the vertices of the quiver. The first term is the dimension of the projective at vertex 0, the second of the projective at vertex 1, and so on. So let me just quickly illustrate how this bijection look like in a particular example. So let's fix the theorem here still, and let's consider an example here. We let B be the path algebra of the linearly oriented A4 quiver, 4 vertices, 3 arrows, and we take the quotient by the ideal generated by the composition of the 2 first arrows. This is an admissible ideal, so you get a Nakayama algebra. And then we will compute the associated cubic series, and it's given as follows. You just compute the dimension of the indecomposable projectives. The one at vertex 0 has dimension 1 because it consists of all paths ending in 0, and there's only one such path, which is the trivial path. This fits very well with the first criteria here, that the first term should be 1. Then the dimension of the projective at vertex 1 has dimension 2 because there are 2 paths going in, the trivial path and the path given by the arrow alpha. Then the dimension of the projective at vertex 2 is also 2. And then dimension of the projective at vertex 3 is 3. We see that all these terms are greater than or equal to 2. And all these terms at each step we increase by at most 1. So we see that this satisfies the condition of a cubic series. And that result also holds more generally for any Nakayama algebra. Okay, so we want to define now a higher version of the Nakayama algebras. And this construction is quite analogous to the definition of the classical Nakayama algebras. Namely, we first define a higher version of the algebra AN we talked about, which was the path algebra of the linearly oriented AN quiver. And then we define the higher Nakayama algebras as certain quotients of this higher analog of AN. So we also, to do this, we first start by defining the higher versions of AN. So we fix somehow the dimension, the higher dimension we're considering. This will, throughout the talk, be this integer d. And then as a first step, we take the tensor product of this algebra AN with itself d times. AN tensor up to AN. So this will be an algebra itself, where the algebra structure, and particularly the multiplicative structure, is inherited from the multiplicative structure of the AN itself. And as an algebra, it can be presented as a quiver with relations, and the quiver of this tensor product is just given by a d-dimensional cube, and the relations are just commutativity relations for each square. So for example, if you imagine the d equals 1 case, you just have the algebra AN, the path algebra of the linearly oriented AN quiver, and you can somehow visually see that that's just given by a line. So I can maybe illustrate this in a couple of examples in dimension 2 and 3. So let's look at, for example, the path algebra A3. Then we can take the tensor product of A3 with itself. According to what I said, this should give us a square, and the square looks as follows. Note that here we have written something on top of each arrow. And what is on top of each arrow is the element in the tensor product which corresponds to that arrow. Note that this tensor product is equal to the path algebra of this quiver with the relation that each square commutes. I've also written some integers at each vertex, and the integer ij in general tells you which primitive idempotent that vertex corresponds to. So the vertex ij corresponds to a primitive idempotent of the tensor product, and it's the primitive idempotent obtained by taking the trivial path at vertex I of A3 and tensoring it with a trivial path at vertex j of A3. So we take the tensor product of two primitive idempotents of A3, and we get the primitive idempotent in the tensor product. Okay, so now we can also look at the case of A3 and the dimension 3 case, and then the tensor product 3 times will now give you a 3-dimensional cube, so just a cube. The quiver will look like this. The relation will be that each square commutes. I've also omitted to writing the vertices, some vertices and some arrows, but there are some vertices and arrow on the back, which you do not see in this picture. Again, the integers here tells you precisely which primitive idempotent in the tensor product they correspond to. Okay, so that tells us a bit about how the quiver with relations for the tensor product looks like. As I said, it's a d-dimensional cube with commutativity relations. We've also seen that the vertices of this quiver will correspond to the primitive idempotents in this tensor product, which is precisely tensor product of primitive idempotents of the underlying algebra AN. So it's tensor product of the following form, where Eij is a primitive idempotent of AN. We saw that in the dimension 2 case in the previous example. Now this holds in general, and in particular, this tells us that the vertices of this tensor product can be identified with a set 0, 1 up to n-1, and then you take the Cartesian product of that set with itself d times. That's this notation. So for example, if you have an element in here, so a tuple I0, I1 up to ID-1, then that tuple will correspond precisely to this primitive idempotent and therefore to that corresponding vertex. So from now on, when I talk about vertices of this algebra, I will just talk about this set. So we want to determine a subset of the vertices, so namely a subset of this set. And this subset will be used in defining the higher analog of AN. And the subset we want to consider is denoted OSDN. I think OS stands for ordered sequences. It should consist of all d-tuples of integers between 0 and n-1, which form a non-decreasing sequence. So that means that the first term is less than or equal to the second term, which is less than or equal to the third term, and so on, up to ID-1. So I will record how this is defined up here. Now, using this, we can define the higher analog of AN, which is typically called the higher Auslander algebra. So these algebras were introduced by Iyama in 2011. His definition looked a bit different, but he also showed that they are equivalent to the definition I'm about to give. So the higher Auslander algebra of type AN, we have fixed some dimension d now, This is given by tensoring, taking the tensor product d times, where d is that dimension, and then taking an idempotent quotient of this algebra we've looked at. And you take the idempotent quotient where you kill all the primitive idempotents which do not lie in this set. So in particular, this tells you that the remaining vertices, the primitive idempotents that do not get killed, are precisely the ones lying in this set. So this set is in bijection with the vertices of the higher Auslander algebra. So before I explain or illustrate how this construction looks like in a couple of examples, I just want to mention some places where this higher Auslander algebra occurs. And in particular, its perfect derived category. So originally, these higher Auslander algebras were introduced in the context of higher Auslander-Reiten theory. But since then, there has been a lot of different contexts where these algebras have reappeared somehow or have been found. And in particular, the perfect derived categories seem to have some kind of play a central role in lots of different areas of mathematics. So let me mention the ones I'm aware of. So it's been shown that the perfect derived category is equivalent to certain partially wrapped Fukaya categories of certain d-fold symmetric products of two-dimensional unit disk with finitely many stops on its boundary. Don't ask me what these words mean, but if you want to know, I suggest you have a look at the paper by Dickerhoff, Hasso, and Lekili, where they show this property. Then it's also been shown that they are equivalent to certain derived Fukaya-Seidel categories of certain family of singularities by Ilaria di Deda. And then it's also been shown that they're equivalent to certain derived categories occurring when you study posets. So derived categories of certain lattice of order ideals of product of two ordered chains. Again, I'm not completely sure. I'm not an expert in those words and in those terminologies, but if you want to know more, you can have a look at the papers by these authors I mentioned here. I should also mention that this last paper, I think, was uploaded very recently, like maybe 2 weeks ago. Yeah, the main point I want to make with this is just that these higher Auslander algebras seems to have some kind of important properties that makes them appear in different contexts in mathematics, and therefore it would be useful to have some way of studying them or develop tools to study them. And that's some of what I want to advocate as a particular consequence of what we are doing in our work. So we are showing how you can get silting complexes from higher torsion classes. In particular, silting complexes give you derived equivalences for this category, and therefore you also get information regarding these different contexts. Okay, so and now let me just illustrate a bit how the construction of the higher Auslander algebra looks like. So let's do our two-dimensional case with A3. Then to determine the higher Auslander algebra of type A3 in dimension 2, we need to determine this set. And this is precisely the set of non-decreasing sequences of integers. So it's the blue vertices here. Now, the higher Auslander algebra is obtained by taking the idempotent quotients of all vertices not in this set. So all vertices which are not blue. And they are precisely here the black vertices. So we kill these vertices. We take the idempotent quotient. And then we are left with the following algebra. So the higher Auslander algebra is the path algebra of this quiver. And then you have relations which are inherited from the commutativity relation of the squares of the tensor product. So of course then the middle square here will commute. But then you also get that the two top triangles give zero relations. And that's because they were previously part of a commutative triangle where one of the vertices were killed. So maybe a lot of you probably recognize this as also the classical Auslander algebra of the linearly oriented A3 quiver. And that's no coincidence. And the higher Auslander algebras were originally defined in similar ways like that. Okay, we can also have a quick look at the three-dimensional case. Then remember we had the equivalent relation of the tensor product look like the following cube as depicted here. We want to determine the tuples of non-decreasing sequences. They are precisely the vertices marked in blue. I also had to mark one vertex behind, which you don't see in the original picture, 1, 1, 1, which is also blue. And then the higher Auslander algebra is obtained by taking the idempotent quotient by the black vertices. So you kill and remove the black vertices, and then you are left with the following algebra. So here the higher Auslander algebra is the path algebra of this quiver. Again, you have relations which come from the commutativity relation of the tensor product. And in this case, still all squares commute. And places where you have triangles, now you have zero, also give zero relation as they were previously part of commutative squares. Yeah, so this gives you some of this algebra. And you can also do this in higher dimensional settings, of course, but it's a bit harder to draw. Okay, so now we've defined the higher Auslander algebras, so the higher analog of AN. Now remember that the Nakayama algebras are quotients of AN by admissible ideals, and the higher Nakayama algebras that we want to define will also be quotient of this higher Auslander algebra, but there is a crucial difference in the one-dimensional case and in the higher dimensional case, and that's namely that the quotients are no longer admissible, but they are idempotent quotients. So an idempotent quotient is never admissible unless it's trivial, because an idempotent quotient contains an idempotent, which is a path of length 0. So if you fix the dimension d, then similarly or analogously to the classical case, we will have one higher Nakayama algebra for each cubic series, Ksn. So each, And for each such cubic series, we can define a subset of the set of vertices of the higher Auslander algebra. Remember, this is the set of non-decreasing sequences. The subset we define of this is denoted OSDL, L indicating it depends on the choice of cubic series, and it consists of all the elements such that you have a certain inequality should hold. Namely, if you take the last term of this tuple of integers, this is yd minus 1, and you subtract the first term, you add 1, then it should be less than or equal to some term in the cubic series. And the term in the cubic series you can find exactly at the spot yd minus 1, which is this last term in this of this element y. So I don't really have a very good intuitive explanation for why this would be the necessary requirement. I think the main point, as far as I understood, is that this is what makes the theory work. So this is what makes the construction of the higher Nakayama algebra, which we give a bit later, why they will still have D-cluster tilting subcategories. Okay, but now let's, I'll get back to that later, but now let's just define the higher Nakayama algebras. So the higher Nakayama algebra associated to such a QP series is defined as I mentioned before, as an idempotent quotient. You take, it's written ADL, indicating it depends on the cubic series. It's defined by first looking at the higher analog of AN, ADN, the higher Auslander algebra, and then taking an idempotent quotient by all the primitive idempotents which corresponds to elements which are not in this set OSDL. So it's quite similar to, it's quite similar to how it was for the higher Auslander algebras, where you killed a certain number of vertices which were not in a particular set you pointed to. And this is somehow the similar situation here. They do not satisfy this condition. In particular, the primitive idempotents that survive are precisely the primitive idempotents corresponding to this subset. So this subset, therefore, is in bijection with the vertices of the higher Nakayama algebra. Okay, so note that if we let the QP series be as large as possible, be maximal at each step, then this inequality will be empty. It will always hold. So this set will just be the set of all non-decreasing sequences. In particular, this quotient is just the quotient by the zero category, and therefore the higher Nakayama algebra is actually equal to the higher Auslander algebra. So higher Auslander algebras are particular examples of higher Nakayama algebras. Okay, so let me just, with that, let me compute some examples. So here I just save the formulas in case you want to study them more carefully. They are just, now let's see what happens in the case of the higher Auslander algebra of type A3, a two-dimensional one. So we want to define a higher Nakayama algebra, so a quotient of this algebra, idempotent quotient. And for that, we need to fix which QP series we are considering. And we consider the one given by 1, 2, 2. In this case, we need to check for which vertices of these depicted here are contained in this subset OS2L, where L is here. And that's precisely the red ones. This is a simple, short computation you can just do. So with this, we see that the higher Nakayama algebra is obtained as an idempotent quotient of this whole algebra by killing the vertex which is not red, which is not contained in here, namely the vertex 0, 2. And then we are left with the following algebra. And here one can easily check that this is just the path algebra of the linearly oriented A5 quiver modulo radical squared. Of course, if you have higher ends and more complicated QP series, then you will get more complicated algebra. So they don't have to be that simple. But okay, let's also look at the three-dimensional case with the same QP series. So here we have the higher Auslander algebra of type A3 in dimension 3. It was given by the following quiver where all squares commute and where the triangles give zero relations. We fix the same QP series, and then we want to look at which elements are in this subset, OS3L, and they are precisely, or which vertices are in, and they are precisely the ones marked in red. So to compute the higher Nakayama algebra, we need to take an idempotent quotient by the ones which are not contained in here, so by the black vertices. And doing that gives us the following algebra. And again, one can check that this is just the path algebra of the linearly oriented A7 quiver modulo radical squared. But for other examples, it will be more complicated. Okay. So what I want somehow to do in this talk is to study the higher Nakayama algebras, or that's one of the problems we will pose ourselves. But there are certain challenges if you want to do this, in particular when d is greater than or equal to 2. For d equals to 1, it's well known that the classical Nakayama algebras often have very easy representation theoretic and combinatorial properties. So if you have some kind of conjecture or something you want to check, it's often very easy to explicitly compute it for the classical Nakayama algebras. For the higher Nakayama algebras, there are more challenges when one wants to study them. So even though they are given by quivers with relations and a quite explicit description, the description is still quite complicated. So as far as I know, it doesn't fall into any class or many classes of combinatorially defined algebras which are easy to study. So for example, they have complicated combinatorics and they are not quadratic algebras in general. They are not gentle in general. They are not biserial in general, and so on. Another challenge or problem is that they also have complicated homological properties. And by that, I just mean that they do not necessarily have global dimension 1. So global dimension 1, and they can have arbitrary large global dimension. So global dimension 1 algebras, of course, have are the hereditary ones, and it's known that the representation theory is easier to study than when the global dimension increases. And then another problem is that they are almost always wild if you have n and d big enough. So there's in some sense no hope in general to be able to classify all their modules. So then we have all these kind of challenges, and you can ask what tools we have. And I want to somehow advocate that we have one very useful tool which one can use to study the algebras, and that's namely the cluster tilting subcategories. So that leads me to the second part of my talk, which is about cluster tilting subcategories. So let A be some finite dimensional algebra, and let mod A denote the category of finite dimensional right A modules. Then we want to say now what a cluster tilting subcategory of mod A, what that means. So this is a definition due to Iyama from 2007, and it's given as follows. So a full subcategory M of mod A is called D cluster tilting if it satisfies three properties. The first property is somehow not very strong or interesting. It just tells you that it's closed under finite direct sums and summands. Another way of phrasing this is just saying that M is uniquely determined by its indecomposable modules, and then it's just the additive closure of its indecomposable modules. This is not a very interesting condition, but it's somehow necessary. The second condition is that this, which is more interesting, is that this is a rigid subcategory in degrees between 0 and d. So it should have no extension in degree 1, 2 up to d minus 1 between any object in M and any other object in M. And then the last condition tells us that any module, A module, can be resolved and co-resolved by objects in M. So in other words, you can find an exact sequence where k is in the rightmost term and rightmost side, and all the other terms are in M, x1 up to xd. So this is what I mean when I say M resolves modules in A modules. And then similarly on the other side, you can find an exact sequence where k is on the left-hand side, all the other modules are in M, and I then say that M co-resolves the modules, the A modules. Yes, as I mentioned, this is a non-standard definition, or maybe I didn't mention that, but in any case, it is a non-standard definition. Normally, you wouldn't have this kind of defined in terms of this property tree, but you would rather say that M is rigid and maximal with respect to rigidity, in the sense that if you have anything else which is rigid and with respect to M, then it has to be contained in M. I prefer this definition. It is equivalent to the original one, but for me this tells me a bit more what the D-cluster tilting subcategory actually is. It's somehow a very well-behaved generator and co-generator by mod A. It's well-behaved in the sense it has a lot of rigidity properties, and also that generator in the sense that any A module can be generated or part of such an exact sequence where everything else is in M, and similarly here. So that's the second. M is somehow well-behaved generator and co-generator of mod A. It's kind of what I want to advocate with this definition. Okay, so important remark is that if D is equal to 1, then you can see in this condition 3 that you get an exact sequence of the form 0, x1, k, 0. In other words, k is isomorphic to x1. In other words, since x1 is in M, as assumed here, k also has to be in M. Since k was an arbitrary A module, this tells us that whenever D is 1, M has to be equal to the whole module category itself. So D equals 1 just recovers module categories of finite dimensional algebras. Okay, so the main point of this definition is, of course, that the higher Nakayama algebras have cluster tilting subcategories. So I next plan to describe how these cluster tilting subcategories looks like. There are some somewhat technical formulas, but I think the main point one should take from this is that one has a d-cluster tilting subcategory, the higher Nakayama algebras, and that you can somehow describe it explicitly. So let me start with the description. So we fix a higher Nakayama algebra. In other words, we fix its dimension and the cubic series determining it. Then we look at the set O as d plus 1L. So note that here d, we have d plus 1 and not d. So we go one dimension higher. And we therefore have d plus 1 tuples. So we choose such an element, and then we claim that we can define a right module, finite dimensional module, over the higher Nakayama algebra associated to L in this dimension d. And it's an indecomposable module. It's the unique indecomposable module, such that for any vertex of the higher Nakayama algebra, remember the vertices of the higher Nakayama algebras are just in bijection with the set OSDL. So it's just a d-tuple of integers with some properties, as we've seen before. So for any vertex, we can evaluate this module at the vertex. So ADL, the higher Nakayama algebra, is given by a quiver with a relation. So a module can also be thought of as a representation of that quiver. And then we want to know what that representation, what value it takes at the vertex y. And this is what I denote here, mxy. And this takes the value of the k-dimensional vector space if you have some slightly complicated interlacing relation, and then 0 otherwise. So this, what this tells you, or what this requirement is that x somehow it is point x0 up to xd minus 1, so you cut out the last thing, is pointwise less than or equal to y0 up to yd minus 1. And then it also requires for y0 to yd up to yd minus 1 to be pointwise less than x1 up to xd, where you cut out the first term. So this is somehow a quick way of writing two inequalities together. Now, this gives you a map from this set OSD plus 1L, ordered tuples determined by this cubic series, to indecomposable modules over the higher Nakayama algebra. And this map is injective on isomorphism classes. So this means that if two modules, mx and mx prime, are isomorphic, then the tuples we started with had to be identical themselves. Okay, so now we have a way of pointing to a certain class of indecomposable modules over the higher Nakayama algebras, these mx. And the theorem I want to state now is basically that these indecomposable modules form the d-cluster tilting subcategory. So this as a theorem is due to Iyama in the case of the higher Auslander algebras, and is extended to by Hasso and Kuhlsammer in 2019 to the higher Nakayama algebras. And it states that the subcategory NDL is depends on the cubic series L, which is just defined to be the additive closure of the image of all these the additive closure of the indecomposable modules M, which we have defined, running over all the elements of this set. And this is a d-cluster tilting subcategory in the module category of the higher Nakayama algebras. So in particular, they satisfy the condition I mentioned on the last page. Again, the main point is that we have a d-cluster tilting subcategory and it can be described quite explicitly. For the cubic series given by the maximal entry at each term, as we saw before, for this cubic series, we just get the higher Auslander algebra back, ADN. So to stick with the same notation, we also let MDN denote the d-cluster tilting subcategory in that case. So this is the d-cluster tilting subcategory associated to the higher Auslander algebra, MDN. Okay, so now let's look at some examples. So we look at the path algebra or the higher Auslander algebra of type A3 in dimension 2, given by the path algebra of this quiver, as we saw before, with commutativity relation and zero relations for the triangles. Then we know from the formula or the theorem on the last page that the two cluster tilting subcategory of the module category of this algebra is just given by the additive closure of these indecomposable modules determined by the set OS33. Here, as I mentioned, the dimension increases by 1. You have a 2-dimensional thing here, but you have a 3-dimensional thing here. So we want to determine this set. And again, we've seen a bit how OS33 looks like, namely, it's precisely the blue vertices as indicated in this 3-dimensional cube. We made that computation a bit earlier. So if we want to look, the indecomposables in this two cluster tilting subcategory correspond precisely to the blue vertices in this quiver, or to the vertices of this quiver. So this is the following statement. But what one can also show is that the morphisms between the indecomposables corresponds to the paths in this quiver modulo the exactly same relation as we had when we defined the higher Auslander algebra. So we have that all squares commute and that triangles give zero relations. This is somewhat illustrating the fact that the higher Auslander algebras can also be obtained iteratively by taking the endomorphism ring of the D-cluster tilting subcategory and then getting a higher Auslander algebra of 1 dimension higher. So this is somehow reflecting that fact. That's why the description is almost identical to the definition of the higher Auslander algebra we saw before. Now we are also looking at the higher Nakayama algebras. They are defined by cubic series. So let's say we have this cubic series, and then we want to determine this subset M2L. This is the additive closure of all the vertices in OS3L. So we need to determine the set OS3L. They are precisely given by the red vertices here. So M2L now becomes the full subcategory of this big category determined by the red vertices. So note that here, this is slightly different from the situation when we had the higher Auslander algebra. The higher Nakayama algebra, because in that case, we took an idempotent quotient. In this case, we do not have any idempotent quotient, we just consider a full subcategory. So as an additive category, this is the full subcategory determined precisely by the additive closure from the additive category determined by the red vertices. Okay, so now we've looked a bit at the D-cluster tilting subcategories for higher Auslander algebras and higher Nakayama algebras, and now we want to talk about higher torsion classes. So first we define them in complete generality. So we look at the D-cluster tilting subcategory of the module category of a finite dimensional algebra. Then we want to define what it means to have a higher torsion class. So this definition was originally introduced by Peter Jørgensen in 2016. It says that the full subcategory U of our M is a d-torsion class if it has the following property. Whenever you choose a module X, which lies in our D-cluster tilting subcategory, we can find an exact sequence. Note that this is an exact sequence of length D plus 2. In particular, D equals 1 will give you a short exact sequence, but in general, you have D plus 2 terms. You have D terms to the right of your X and 1 term to the left of your X. And then you have your original X you chose here, second to the leftmost spot. The requirement of this exact sequence is, first of all, that all these terms on the right should be in M, and also this thing should be in M. So this whole thing becomes an exact sequence of A modules where each term is in M. Now, this condition that Ux is in M is actually a bit stronger. Namely, we want it not just to be in M, but also in this full subcategory we're defining. this d-torsion class we're defining. So that's one part of the condition. And then the second requirement is that whenever you apply the hom functor, hom AU, where U is some object in our d-torsion class, and you apply that to this complex on the rightmost side, y1 to yd, then this should give you an exact sequence. So this was the Jørgensen's definition was motivated in order to generalize the classical situation. In particular, for d equals 1, one can check that one actually recovers classical torsion classes, which we will have a quick look at. So first of all, for d equals 1, we saw that a 1 cluster tilting subcategory is just the same as a module category itself. So we are looking at full subcategories of the module category, and we say they are a one torsion class if and only if these conditions hold when d is equal to 1. And that means that for every A module X, we can find an exact sequence. Note that now this is a short exact sequence, as denoted here. There's only one term on the right, namely y1. And the requirements here is first and foremost that ux is in U in the full subcategory. And then we also have the requirement that this complex is exact when d is 1. And that just corresponds to this complex being exact. And that's just the same as saying that this morphism space is 0. So from this, one can see that one recovers precisely the somehow classical definition from Dixon of a torsion class. So this gives a generalization of the torsion classes. Now let's just have a quick look at an example. So I just want to illustrate, and even for simple algebras, you can get a large class of examples of two torsion classes. So let's look at this two cluster tilting subcategory determined by this cubic series L. So this is the two cluster tilting subcategory of A to L, the higher Nakayama algebra of dimension 2 determined by this cubic series. And I'll just list down all the two torsion classes. Yeah, first and foremost, you have the whole category itself, and you have the category full subcategory which only consists of the 0 object. There are some other always exist, those examples. Then you have additive, the ones generated by a single indecomposable module. So you have the additive closure of the indecomposable at 0, 0, 0, at 1, 1, 1, and at 2, 2, 2. Then you have the ones generated by two indecomposable modules. So you have these two, you have the twos at the end, and you have these two. Then you have the ones generated by three indecomposables. Then you have the one generated by four indecomposables. Here, 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 and here, and here. Then five indecomposables, and then six indecomposables, which shows you just that you get a rich theory of subcategories with this definition. Now I want to explain to you how, from a d-torsion class, you can obtain a silting complex. So this maybe can be one motivation for why one would want to consider this definition, is that it actually gives rise to silting complexes. So before I start, maybe I should just say that this construction is very analogous to the classical construction, going from a functorially finite torsion class to the associated two-term silting complexes by Adachi-Iyama-Reiten, which is basically you go to an X1 projective generator, which is the same as the maximal tau rigid module generator, and then you take a projective presentation of that. So you take a projective presentation of the maximal tau rigid module or the X1 projective generator, and then add the support part. Here it's similar, except you replace the integers 1 by d and the length 2, the projective presentation, by length d plus 1. So I first need to tell you quickly what is an XD projective. And that's precisely an object U or a module U, if you want, in the d-torsion class is called xt projective if it has no extensions in degree d with any other module in the d-torsion class. So, and here U should be on the right, basically like the projective side. So note that this extension group would always be 0 in degree 1 to d minus 1. And this is just because U is a full subcategory of M, and one of the assumptions on M was that it was rigid in degrees between 0 and d. So this is somehow the first extension group where it could potentially be non-zero. And the requirement is that it's still 0 in that degree. That defines xt projective. Then we let mu be somehow a basic additive generator of the xt projectives. So it's just a sum of all indecomposable xt projectives in U, and you take one indecomposable for each isomorphism class. Then you take the associated d+1 projective presentation of mu. And what do I mean by that is that you take a minimal projective resolution, of this module mu, and then you stop after d+1 steps. So you just look at the d+1 first terms in the minimal projective resolution. For example, for d equals to 1, this will precisely be a minimal projective presentation of mu. Finally, you define the support part. That's a projective module pu, and it's a sum of all the indecomposable projectives, one for each isomorphism class, of satisfying the following quality, namely that they have no maps to our d-torsion class U. This is this equality. So in other words, this is our basic additive generator of the projective modules satisfying this property. So with this terminology, we can now state the main theorem, or one of the main theorems of our work, which is tells you, given a d-torsion class, how you can get the associated silting complex. So basically there exists an associated silting complex. So that's the theorem by the 6 authors, and says that if you have a functorially finite d-torsion class, then the complex PMU, which I just described, the minimal projective d presentation from the basic additive generator of the xt projectives. If you look at that complex and you add the support part as defined here, shifted in d degrees, so the classical case it would be 1 degree, here it's d degrees, then this gives you a silting complex in the category of perfect complexes of A. Note that here we have this kind of additional adjective, functorially finite. I think this is maybe also sometimes called pre-covering and pre-enveloping. This additional assumption corresponds, of course, to the functorially finite torsion classes in the classical case. It is not very strong in the situations we're looking at in the higher cases. In fact, for most D-cluster tilting subcategories I know about, for module categories, they are themselves only consist of finitely many indecomposables. So this property will then always hold for any subcategory. Now, the highlight of this result is that you get now derived equivalences from A to proper connective DG algebras, basically the DG endomorphism ring of this complex. And sometimes these things will also actually be proper algebras themselves when you have tilting complexes. Now, if D is equal to 1, this is what I mentioned in the beginning, then this recovers the bijection between functorially finite torsion classes and two-term silting complexes due to Adachi-Iyama-Reiten. At least it recovers one of the maps in the bijection. It's important also to mention that in the higher case, there is no bijection, or at least we do not know of any, and we haven't been able to show any kind of natural bijection. So from the construction, it is not hard to see that the map associating a functorially finite d-torsion class to a silting complex is an injective map, meaning that if you have two different functorially finite d-torsion classes, you get two different silting complexes. However, we do not know how to characterize the image of this map. We do not know how to characterize the silting complexes, which arises from functorially finite d-torsion classes. I believe it will be very interesting, but we don't yet know how to do this. And then just to repeat what I said before, this assumption about being functorially finite is not very strong. For example, for the higher Nakayama algebras, all d-torsion classes are functorially finite. So in some sense, for those algebras, you could skip that assumption. Okay, so our goal now is to apply this result to higher Nakayama algebras. Basically, we have a combinatorial description of the higher Nakayama algebras, and we want to have a combinatorial description of the silting complexes that arises from the functorially finite d-torsion classes using our theory. And to do this, we first need to go via the d-torsion classes, and we show that there is a combinatorial description of the d-torsion classes, and then we can explicitly compute also combinatorially the associated silting complexes. And the advantage of doing all this is that you can plug it into a computer. And we develop a small program which can take in a higher Nakayama algebra or a higher Auslander algebra, and which can spit out the collection of all d-torsion classes and all the corresponding silting complexes for these d-torsion classes. So this you can, for example, apply to the higher Nakayama algebras, the higher Auslander algebras, which we first defined. So my plan now is to somehow explain a bit how the combinatorics looks like, and also how this combinatorics of the silting complex and the d-torsion classes look like. Maybe the important thing is not to remember explicitly all the formula, but just that there are explicit formulas, and you can look them up if you want. So we fix a higher Nakayama algebra, and basically then means the cubic series and some dimension, the higher dimension we're considering. Then we need to define a couple of some relation on the collection of d+1 tuples of integers. And we say that x is squibbly arrow y, or x is interlaced with y, if you have the following inequalities. It looks a bit like the inequalities defining the indecomposable modules, which we looked at before. It's not completely the same. What it is saying is that x is pointwise less than or equal to y. So it consists basically of two inequalities, namely that x is pointwise less than or equal to y, and that y is pointwise less than or equal to a shift of x. So x0 is less than y0, x1 is less than y1, and so on. But also that y0 is less than x1, so x shifted by 1. y1 is less than x2, and so on. Then you also have an automorphism on the set of d+1 tuples of integers, just given by subtracting 1. And this is denoted tau d because it corresponds to the higher Auslander-Reiten translation, for those who know that one. And then we see that given a subset I of the indecomposable modules of the D-cluster tilting subcategory, we can define, and we have an associated full subcategory, which is just the additive closure. So this association I to ui basically gives you a bridge between the combinatorics on the one side, the subset I of OSD+1L, and the homological algebra on the other side. So this, or the category theory on the other side, the subcategories of the D-cluster tilting subcategories. And we characterize precisely which I's correspond to d-torsion classes. So this is a theorem which was recently accepted for publication, and you can find it on arXiv. It's part of some other results we have in the same paper, and it says that gives a precise description of the d-torsion classes if and only if they are given by subsets I here, where I needs to have two closure properties. this, I'll just quickly state them. You don't really need to memorize them, as I mentioned, but just know that they exist. The first one is that whenever you have an element in I, and an element in the ambient set, such that X, the element in I, is pointwise less than or equal to the element Y, and they're equal at the last term, then Y has to be in I. And the second condition is that whenever you have two elements in I, and you have this kind of squibbly arrow between them, this kind of relation, where when you are looking at tau d of one of them, then any element Y such that it component-wise is equal to either xi and zi at each term, any such Y has to be in I. So for those of you who know what this means, the first property basically says is closed on the d quotients, or is the combinatorial equivalent of that. The second one is the combinatorial equivalent of being closed on the d extensions. Okay, so now in the last minute, I will say something about how you can get a QP a silting complex explicitly from the higher torsion class. So again, we fix the higher Nakayama algebra, so the QP series and the higher dimension, and we fix a subset defining a d-torsion class. Then we need to define the xt projectives and the support part first before defining the silting complex. They are just explicit sums of indecomposable modules defined by explicit sets IP and J, given by a certain formula that I don't want to get into, but you can look it up if you want. And this gives us the xt projective and the support part. To compute the silting complex, we also need to take the minimal diff projective presentation, and the minimal diff projective presentation of any indecomposable has an explicit formula, which you can find in the paper by Hasso and Kuhlsammer. Again, I don't want to get into the details of this formula. I just want to emphasize that it exists. And then you can just plug in all these formulas to obtain from a given I corresponding to a d-torsion class. So having those two properties, you can plug in all these formulas to get a complex p bullet mx, where you sum over all x in I1, where I1 here, this should be IP, and this should be J, so there's a small typo here. This should be IP, and this should be J. Anyway, you sum over all x in I1 via this formula, and all y in J via this formula, and then you get a silting complex. So this, as I mentioned, can be put into a computer, and it can we developed a program which could calculate silting complexes, and that's precisely the following. This is an example of the output in the case of the higher Nakayama algebra associated to this 1, 2, 2. Here are the two torsion classes I mentioned, and here are the associated silting complex with the associated indecomposables at each degree. And you cannot do this also for more complicated examples. Thank you. I went a bit over time, but thank you very much. And that's all I wanted to say.
Thank you, Sondre. Let's all unmute ourselves and give the speaker a round of applause now. Okay, if you have any questions for the speaker, please ask them now.
I see Hugh has a hand.
Yeah, go ahead. You.
Thanks. Thanks for the lovely talk, Sondre. That was really that was great. My question is, so Stefan Opperman and I some years ago studied the tilting objects and cluster tilting objects in this setting, and so correct me if I'm wrong. It seems like it should be clear that the tilting objects should correspond to a subset of your silting objects.
Maybe, but I don't remember exactly how the tilting complexes when you work with Stefan, how they look like. I know they're not. Sometimes it seems like we might not get all the possible silting complexes that could be natural occurring in higher Auslander-Reiten theory. So I'm not.
Oh, I see. So you're getting some of them,
Yeah, I get
And
it.
so it's not clear that we're getting the same ones. I see.
It might
But-
be. I just haven't checked the formula, so
Yeah,
I'm
okay,
not confident saying that at least.
Yeah, okay. I mean, it seems interesting. Well, assuming that they do, I mean, assuming that that ours are a subset of yours, we studied the poset structure on them, and there's been subsequent work by Nick Williams also on that poset structure. It would be interesting. I think it would be interesting to relate the poset structures, but I guess a first step would be just to understand if there really is an inclusion, and
yeah. For example, I think there is not. How does this work? There should not be a bijection between. For example, these things are often less than, for example, the number of higher wide subcategories for the same algebras, and also I think it should be. How does this story go? Yeah, I don't know, but yeah, I agree. A first step would be to check if they are subsets or the same or coincide in some way, and then yeah,
okay,
it's an interesting question.
yeah, okay, great, thank you.
Thanks, Hugh. Any other questions? Anybody? Did you say at the start, when you were talking about the triangulated categories, the direct perfect category was equivalent to that motivation to obtain the silting complexes was to study that equivalence?
So okay, now I have to go far back. So you meant I mentioned some equivalence between the perfect derived
Yes,
complex
yeah,
and the higher Auslander algebra. I mean, our motivation was not that, but it's something we discovered, and which I think, in some sense, you get a lot of derived equivalences just plugging in all this machinery, and just by switching out the silting complexes, and then it would be interesting to know in which way this could tell you something about these other settings where you have equivalent categories. But yeah, we haven't looked at that. I don't know if that answers your question. Maybe
I mean, it wasn't really a question. Yeah, it was just like your comment. And is the analogous approach, not exactly approach, like with I don't know, pure injectives? I mean, can one go anywhere?
How does that go? I don't know that story so well.
Pure silting, yeah. Like, isn't there like a folklore conjecture about co-silting complexes and pure injective? Ooh.
Maybe, but I don't know.
No, it's okay. It's okay. It's really, yeah. Any other comments or questions? Yeah, it wasn't really a question. Like I was thinking something else. Sorry. I mean, we are here in mod A for some very particular classes of A, and anyway, it doesn't really matter. Right. If we don't have any more questions, let's thank our speaker once again. We don't have a talk next week. We will have Bertrand tomorrow, the week after. Okay. Bye-bye.
Thank you.
Thank you again, Sondre.